Is evolution as vast and random a process as we've often been led to believe? Maybe not. Here's an Undeception's instant expert. Ard Louis is Professor of Theoretical Physics at the University of Oxford, Department of Physics, and he specialises in self-assembling DNA, theories of evolution, the dynamics of soft matter, and machine learning. Imagine being that kind of nerd. And he says that most people think evolution means every possibility is being randomly generated and nature just selects the fittest one. But according to Ard, the outcomes are far more ordered than we think.
One of the ways of thinking about this is, what is evolution really doing when it randomly mutates those genes? Well, remember that you are not your DNA. Right? So just because the genes are random doesn't mean that the outcomes of those random processes are random. And a very simple way of thinking about this would be to think, I'll actually take a step back. Let me give you a very simple biological example that can help explain this. So if you look outside in my garden, you'll see various trees. And I have a walnut tree and a birch tree, and they have very different shapes. Now, interestingly, that walnut tree's shape is not encoded in like a blueprint in its DNA. There's not like a little shape of the tree, put a leaf here, put a branch there. Instead, the tree has an algorithm that basically makes leaves a certain probability, branches a certain probability, and if you run that algorithm, then you get that shape comes out. The birch tree has a slightly different algorithm, which gives it a kind of more flowing birch shape. And so there's no blueprint in DNA, it's actually an algorithm. An algorithm is a fancy word for like a computational program that's being run. And so now imagine that there is a mutation to that algorithm. Okay? It might be that actually a small mutation in the algorithm changes you from walnut shape to birch shape really quickly. Or it may be that it's really hard to go from walnut shape to birch shape. And so to understand that, you shouldn't look at the shape of the trees, but rather try to understand the algorithms. Like a simple change to an algorithm is, for example, now double this process, makes something twice as big, right? That's one little line change and a huge outcome happens. If I randomly change that program, I might see very big changes happening in certain directions and very small changes happening in other directions. So what I'm saying is the mutations are random, but the outcomes are highly non-random. Our idea that we've been developing over the last few years is that if you think about these algorithms, if you think about mutations at the genes really effectively being mutations of the algorithms, then what's going to happen is, if you need to evolve some kind of new phenotype, let's say the walnut tree needs to change into a more birch-like shape because the weather changes or the climate changes, then what's going to happen is it's going to randomly tweak that algorithm, and the first algorithm that it finds that does the job roughly okay is the one it's going to pick. Now let's think about symmetry. So right here in my kitchen, you can see in the tiles on my floor, and they're regularly placed. So if I say to you, come please tile my kitchen, it's much easier for you to say, take this pattern and repeat it n times. That's a short description. I could also tile my kitchen with every tile in a slightly different place. Okay, I'd have to give you a blueprint of every tile. That's a lot of information I need to give you. Now imagine that I am just randomly making tile assembly programs to assemble the tiles of my kitchen. I'm much more likely to find a simple program, because it's just a few lines to describe, than a long, complicated program. So that's the argument. If I randomly search in the space of tiling algorithms, so tell me how to tile your floor, I'm much more likely to find a symmetric way of doing it than a non-symmetric one. So we've looked, for example, at lots of properties of nature and seen there's huge amount of symmetry there. And the question is, why is that symmetry there? We're saying, well, it's just there because it's easy to find.
If you've enjoyed the chance to become an instant expert, then you'll find much more, plus a bunch of other informative videos over at the Undeceptions YouTube channel. Just go to YouTube and search for Undeceptions. See ya.